Welcome back to the deep dive. Today, we're jumping into something really fundamental. Dark matter. Still one of the biggest puzzles out there.
Absolutely, it's everywhere, supposedly, but completely unseen.
Right. But what if there was this kind of wild new idea, a theoretical object called a dark dwarf, that might actually be powered by dark matter?
It sounds like something straight out of science fiction, doesn't it? But yeah, that's the proposal.
Exactly. So our mission today, let's unpack what we think dark matter is, how these, well, hypothetical dark dwarfs could even form.
And crucially, how scientists are thinking we might actually spot them. Find a potential shortcut to understanding this massive missing piece of the cosmos.
Okay, let's get into it. The big problem with dark matter, as you said, it's just elusive.
Completely. It doesn't emit light, doesn't reflect it, nothing.
We only know it's there because we see its gravity pulling on stars and galaxies, right? Like footprints in the cosmic dust.
That's the only way, yeah.
Yeah.
Decades of searching, and still no direct, gotcha moment. No particle detected in a lab.
So if we did find something direct, maybe through these dark dwarfs, how big a deal would that actually be? What changes?
Oh, it'd be monumental. Seriously. We're not just talking about, finding a new particle.
It's more fundamental.
Way more. It could rewrite our basic understanding of physics, how the universe is structured. I mean, it's potentially Nobel Prize territory, a total paradigm shift. Really profound stuff.
Wow. Right. So if it's that hard to find directly, how could a brown dwarf help? Let's talk about those first. What exactly are brown dwarfs?
Right. So brown dwarfs are these interesting middle ground objects.
Like not quite planets, not quite stars.
Exactly. They're bigger than gas giants like Jupiter, but they don't have enough mass, enough gravitational squeeze to kickstart nuclear fusion in their cores.
The fusion that powers stars like our sun.
Precisely. So they don't ignite. They just sort of form, cool down, and drift through space as these big, dim, relatively cold worlds. Failed stars, essentially.
Failed stars, okay.
And what's really fascinating here, the twist, is that these failed stars, these brown dwarfs, might unexpectedly be the key.
The key to finding dark matter. How?
Well, that brings us to this new hypothesis. It's a really clever piece of thinking.
So this is the dark dwarf idea. Tell us about that.
Yeah, so some astrophysicists in the UK and the US, they've proposed that maybe, just maybe, brown dwarfs could transform.
Transform into dark dwarfs.
Into dark dwarfs, exactly. The idea is if a brown dwarf happens to be in a region with, a lot of dark matter.
Denser than average.
Right, denser than average, that dark matter could actually sink into the brown dwarf and accumulate right in its core.
Huh. Okay, dark matter inside a brown dwarf, but how does that power it?
Well, this is where it gets specific. This whole idea hinges on dark matter being a particular type of particle.
Okay, what kind?
Something called WIMPs. Weakly interacting massive particles. They're one of the main candidates for dark matter.
Why WIMPs?
Because, as the name suggests, they'd interact very weakly with normal matter, besides gravity. That's why they're hard to detect. But, crucially, they would interact with each other.
Okay.
And the theory goes, WIMPs are their own antiparticles. Meaning if two WIMPs bump into each other, poof, annihilation. They destroy each other in a burst of energy.
Okay, like matter meeting antimatter.
Exactly like that. So if you get enough WIMPs collecting in the core of a brown dwarf...
They start annihilating each other.
They start annihilating, releasing energy. Jeremy Sackstein, one of the researchers, he put it quite clearly. He said something like, these objects collect the dark matter. The more dark matter you have around, the more you can capture. And the more dark matter ends up inside the star, the more energy will be produced through its annihilation.
So this energy... It wouldn't make it shine like the sun, I guess.
No, not nearly that bright, but it would provide more heat and light than a normal brown dwarf just passively cooling down. It keeps it hotter and brighter for longer.
Right, making it more stable maybe? Less prone to just fading away?
Precisely. And that connects to the really big picture idea here, because this annihilation could provide a steady, constant energy source. These dark dwarfs could be, effectively eternal.
Eternal. Wow.
Yeah, they wouldn't just cool and fade over billions of years like regular brown dwarfs.
Yeah.
They'd maintain a constant size, temperature, brightness, powered by this dark matter fuel, almost indefinitely.
That's mind-bending. But, okay, the million-dollar question then. How would we ever know? How could astronomers actually find one of these theoretical dark dwarfs?
Right, how do you prove it? The proposed method is actually quite ingenious. It involves looking for a specific element, lithium. Specifically lithium-7.
Lithium-7. Why lithium?
Well, see, lithium-7 is quite fragile. Inside a real star, where temperatures are incredibly high due to fusion, lithium burns away really quickly. It gets destroyed.
Okay, so stars don't usually have much lithium left on their surface.
Not much, no. But in cooler objects, like brown dwarfs, where fusion isn't happening or is very limited, lithium-7 can survive. It sticks around.
Ah, so finding lithium-7 is already a way astronomers identify brown dwarfs.
Exactly. It's one of the key tests. If you see lithium-7 in an object that's sort of star-sized, it strongly suggests it's actually a brown dwarf, because a true star of that mass would have burned it all away.
Okay, so where does the dark matter part come in? How does that change things?
Right, here's the clever bit. Imagine you find an object. Thanks to the dark matter annihilation energy, it looks maybe bigger and definitely brighter than a typical brown dwarf of its mass should be. It might even look as bright as a small red dwarf star.
Okay, brighter than expected for a brown dwarf.
But crucially, when you analyze its light, you still find that telltale lithium-7 signature.
So it looks like a small star in brightness, but it has the lithium fingerprint of a brown dwarf.
Precisely. That unique combination, unexpectedly bright for its likely mass, plus the presence of lithium-7 that would be the smoking gun.
The signal that says, I'm not just a brown dwarf, I've got a dark matter engine inside.
That's the idea. That specific mismatch would be the target for astronomers, and finding that would be, well, incredibly strong evidence for WIMPs and therefore for this type of dark matter. It's a very distinct fingerprint they're proposing.
Okay, that is genuinely clever. But let's be real, there have to be some big ifs here, right?
Oh, absolutely. A lot of ifs. Huge ones.
Like, first off, this whole thing relies on dark matter being WIMPs specifically.
Correct. If dark matter turns out to be something else, like maybe axions or sterile neutrinos or dark photons, these other theoretical particles.
Then they wouldn't annihilate and you wouldn't get this extra energy.
Exactly. There'd be no way to tell from the outside that dark matter was accumulating inside the brown dwarf. So the nature of dark matter itself is the first big if.
And I guess the biggest if of all
Is whether dark matter, in any form we currently theorize, actually exists.
right. There's always the possibility that the gravitational effects we see are due to something else entirely, some modification of gravity maybe, some unknown physics.
That possibility is always on the table. It's less favored by most physicists based on current evidence, but you can't rule it out. Finding direct evidence like this dark dwarf signature would be huge for ruling in particle dark matter.
Which is why it's so important, I suppose, to keep generating these different ideas, different theories about what dark matter could be, and crucially, different ways we might detect it.
Absolutely essential. You need a wide range of experiments and observational strategies. Some looking for WIMPs underground, others looking for axions with magnetic fields, and now maybe astronomers looking for these weird bright brown dwarfs.
Canting a wide net.
Exactly. You investigate all plausible avenues at once, that maximizes the chance of actually finding something.
So where do the researchers suggest we should look for these potential dark dwarfs?
They suggest the best hunting ground would be towards the center of our Milky Way galaxy.
Because that's where dark matter is thought to be most concentrated.
That's the thinking, yeah. Higher density of dark matter means a higher chance of it accumulating in brown dwarfs there. For anyone interested, the paper with the detailed calculations is up on the ArcSieve preprint server, and it's going to be published in the Journal of Cosmology and Astroparticle Physics.
Good to know.
Yeah.
So summing up this dark dwarf idea, it's a really fascinating sort of out-of-the-box approach to the dark matter problem.
It really is. It highlights that scientific creativity,
Yeah.
Taking known objects like brown dwarfs and asking, what if?
It's a novel pathway in this decades-long search.
Definitely. And it makes you think, doesn't it? It leaves you with this thought. Imagine how many other secrets might be hidden in the universe, maybe disguised within objects we think we already understand.
Just waiting for us to look at them in a new way.
Exactly. It's a good reminder to keep questioning, keep looking, keep exploring those deep cosmic mysteries. There's likely so much more to uncover.
A perfect thought to end on. Thanks for joining us on this deep dive into potentially glowing dark dwarfs and the ongoing hunt for dark matter. We'll see you next time.
Welcome back to the Deep Dive. Today,